Hey all, I'm going to make a video here to help explain this example using a model. So during lecture I'm just sharing my screen. You can't really see any of the models. It really helps to see those in 3 dimensions, especially with the Newman projections because they are a challenging issue for students. So if I'm given a problem like this, the first thing I want to do is to look at the Lewis structure, or in this case the bond line structure, and make sure I can make a model that matches the 3-dimensional positioning of all these atoms in space. So I want any atoms that are connected with a regular line to all be in the same plane. And then this has a dashed wedge here rather than a solid wedge. And so the dashed wedge indicates that the group is pointing away from me. So I want 1, 2, 3 carbons and the chlorine all in the same plane, and then a 4th carbon pointing away. So when I look at my model, that's the situation I have. I put 1, 2, 3 carbons and the chlorine all in the same plane. And notice the other carbon is pointing away from me. That's the one with the dashed wedge. Right, so when I've got those 3 atoms and the chlorine in the same plane, this other carbon back here, this one back here, is pointing away from me. And so now I can see that that molecule matches the structure on the screen. 3-dimensionally, the atoms are attached in the same positions as the molecule on the screen. The next thing I want to do is to make sure I correctly draw the Newman projection based on where the observer is looking. So if I count this chain 1, 2, 3, 4 carbons, I'm looking down the carbon 2, carbon 3 bond. So I need carbon 2, which does not have the chlorine, and carbon 3, which does have the chlorine, to be eclipsing one another in my model. So I find the carbon 2, the one that does not have the chlorine. Carbon 3 does have the chlorine, and I rotate it so I'm looking down that axis with both of those atoms attached there. So now hopefully you can kind of see how I can make this into a Newman projection. So here's the molecule as it was looking on the PowerPoint slide, the 3 atoms and the chlorine all in the same plane and the other CH3 group pointing away. So I basically just rotate my position from which I'm viewing it. And now I'm looking down the carbon 2, carbon 3 axis, and the chlorine is on carbon 3. So this is the angle I'm looking down to draw my Newman projection. The front carbon is represented with a point in the middle of my Newman projection. The back carbon, back here, is represented with the circle around that point. The front carbon has a CH3 group pointing straight down. So on the front carbon, I draw my CH3 group pointing straight down from that. The back carbon has the CH3 group pointing down and to the left. And so I draw that down and to the left. Notice this line doesn't come all the way into the circle. It stops here because this bigger circle is representing the back carbon. And then clearly I have the chlorine on the back carbon, so I draw that there coming straight up from the back carbon. So that's how my Newman projection matches the molecule. So notice the second question on the slide here says we want to draw the Newman projection viewing it from the opposite direction. So that would be, instead of viewing it from where the eye is pointing down, I'm viewing it in the opposite direction. So here I'm viewing it from the carbon 3, carbon 2 bond. I'm viewing it up in this direction, so the chlorine is on the front carbon. So if I want to view my molecule from that direction, I've either got to rotate myself around in space, or I could rotate the molecule. So I want to look in the opposite direction. So I'm just going to rotate this 180 degrees, and now I'm looking down the carbon 3, carbon 2 axis, right? So this is carbon 3 in the front, and carbon 2 is back here. The chlorine is still on carbon 3. So now I want to draw this Newman projection. So I've got this front carbon now with the chlorine coming straight up. So that's my front carbon with the chlorine coming straight up. What else is on the front carbon? The front carbon has a hydrogen pointing down to the left and a methyl group pointing down and to the right. So I draw that on my structure. Hydrogen down to the left, methyl group down and to the right. The back carbon has a couple hydrogens pointing up to the right and left, and the back carbon has this methyl group pointing straight down. So on my back carbon, which is the larger circle, I've got the methyl group pointing straight down, and the 2 hydrogens pointing up and to the right and to the left. So that would be the Newman projection. That's the opposite direction viewpoint from the first one we drew. So if we're looking at this molecule, you may be noticing that, especially if I highlight this area of it here, this methyl group here and this methyl group here are kind of close together. Their hydrogens are kind of close to touching, and the electron cloud surrounding these hydrogens is full of electrons. So when this full electron cloud and this full electron cloud get close together here, they start to repel, it becomes unstable. So I may give you a structure like this and also ask you to draw the Newman projection for the most stable rotation for this structure. So if I rotate the molecule in space by flipping it over like a pancake, that doesn't change its stability. I still have the hydrogens over here getting close together and repelling. So to make a more stable rotation, we're talking about flipping carbon-carbon bonds. So here we're talking about rotating the structure to get those hydrogens away from one another. So I want to spread out all of the atoms as much as possible so they're not repelling nearly as much. And then to draw the Newman projection, I want to look down the axis of 2 of my carbons, and depending on how I have the molecule rotated around, it might look differently. But here we're looking down this axis, and what do I see in this situation? On the front carbon, I see the chlorine coming to the left, a hydrogen coming to the right, and a methyl group pointing straight up. So my front carbon in the Newman projection, I have the chlorine coming down to the left, the hydrogen coming down to the right, and the methyl group pointing straight up. So we can see that again here on the back carbon, the one I'm holding with my hand. You see 2 hydrogens kind of pointing up to the right and left, and a methyl group coming straight down off that back carbon, right? And so that's represented in my Newman projection as well. 2 hydrogens pointing straight up and the methyl group pointing straight down. So notice in my Newman projection really allows me to see the stability here. This big methyl group and this big methyl group, they're not huge, but they're big enough where if they come close together like they were over here, this distance torsional angle between these 2 methyl groups brings them close enough together where they repel a little bit. Here, the torsional angle is 180 degrees. They're on opposite sides. That alleviates a lot of that repulsion and makes it significantly more stable.